Okay, so today we're going over periodicity. So periodicity is basically just what it says right here. It's a fancier word for periodic trends, or in other words, trends or patterns that occur throughout the periodic table. Now, periodicity is all based on what we learned last time, which was Coulombic attraction. And remember, Coulombic attraction is just the attraction between the protons and electrons. So again, you have two factors that affect Coulombic attraction. You have distance and you have your quantity of charges. And if you remember from last time, while you were doing the activity, you should have figured out that the distance is the more significant or important factor when determining Coulombic attraction. Okay, so distance is more important. And in terms of our atom, so distance has to do with our energy levels, or number of energy levels, number of energy shells, and then the quantity of charges has to do with your number of protons. Okay, so if you look at the trend for atomic or Coulombic attraction, basically attraction should increase. Your Ca or your Coulombic attraction should increase as you go left to right because you're adding more protons. And then it should decrease as you go from, sorry, let me redraw this. Your Coulombic attraction should decrease as you go downward because you're adding more energy levels, which is more distance. Okay, so it's not really something like you should have to memorize. It's more of if you understand the idea between distance and charges, quantity of charges, then you should always be able to figure it out. But if it helps, like if you're the type that just kind of likes just straight up memorizing things, I guess you could just memorize this if you want to. But I would say it's more important if you understand this idea, you should always be able to figure it out. Okay, so this is going to lead into our next periodic trend, which is atomic radius. So atomic radius, all it is it's just the distance from the center of the atom to the outermost electron or to the valence electron. And basically atomic radius is synonymous with atomic size. So all it's talking about is how big is your atom. So if you look here, you can kind of see the trend for atomic radius or atomic size. So you can see your atomic radius gets bigger as you move down the periodic table. And that should be pretty intuitive. So the reason why it gets bigger as you move down the periodic table is because you're adding more energy levels or shells. Right? So if you add more energy levels, then obviously your atom is going to get bigger and bigger. But if you notice here, if you're in the same period, you see something interesting, which is that even though like lithium and beryllium or lithium and fluorine, they technically have the same amount of energy levels or energy shells. So like you would assume that your energy levels stay or your atomic radius stays the same. But what actually you see happening is your atomic radius actually decreases. And the reason why is as you go left to right, you have more protons in the center, which means you have more Coulombic attraction, which means your protons pull your electrons closer. So the protons are actually pulling the electrons closer to itself as you increase the amount of protons, right? So it makes your shell get smaller and smaller. So as you go left to right across a period, your atomic radius is going to start decreasing. So this is kind of like the table, right? So again, atomic radius. So this is like two ways to say the same thing. Atomic radius, it basically increases as you go left and then as you go down. So atomic radius is the largest over here on this bottom left-hand corner, and then it would be the smallest the closer your element is towards this top right-hand corner. And I would say again, like if you're the type to just memorize this, you can just memorize one of the corners. So I usually just memorize the largest corner. So I just memorize that atomic radius is largest here, and whatever element is closest to this corner would have the larger atomic radius. But also, like especially if you're taking AP Chem, I would say it's more important to memorize the reasoning why, not so much as just memorizing where it is, because that'll help you more. But up to you on what you want to do. Okay, so let's answer this first poll question. So try to answer these questions. Okay, so you can see it's pretty straightforward. You just kind of follow the table. So larger atomic radius, lithium or potassium. So lithium is here, potassium is here. Potassium has more energy levels, so it would have the larger atomic radius. Same thing with these elements here. So these are just looking at the other alkali metals. So you have lithium, rubidium, cesium, sodium. So cesium again has the most energy levels. So your alkali metal that has the largest radius would be cesium. And then out of these elements here, so all of these elements in period 2, you have nitrogen, oxygen, fluorine, and lithium. The smallest atomic radius would be fluorine because it has the most protons out of these. So fluorine would have the smaller atomic radius. Okay, determining the radii of ions. Now, when you determine the radii of ions, you can't just follow this chart because this chart is for neutral atoms. It's not for ions. So cations will have a smaller atomic radius. And in case you forgot, cations are your positive ions. Anions are your negative ions. So cations will have a smaller atomic radius. Anions will have a larger atomic radius. And the reason why is because of something called, it's because of the electrons repulsing or pushing each other away. So what I mean by that is if you have an anion, that means you've gained electrons. And if you have more electrons, then your electrons are going to repulse or push each other away, which would in turn expand your shell. So if you add more electrons, then you have more electrons kind of like repulsing or pushing each other. And that should mean your shell should get bigger in a lot of the cases. So let's go over this. Which of the following would have the greatest atomic radius? I'm going to let you guys do this on your own, but I'm going to just draw the Bohr model for you guys. So whenever you're determining the radii of ions, I would say you need to draw the Bohr model to kind of make your decision on what's happening. Or you can just memorize this fact. But I would say drawing the Bohr model is like a little bit, I guess, more intuitive. Okay, so if I have lithium, so I'll draw the neutral one in the middle. Right, so neutral lithium has three electrons. So if you have lithium positive, that means you've lost an electron. And then lithium negative means you've gained an electron. So take some time to answer this poll, and then also you can try this next question on your own. And I say if you're confused on this next one, you should draw the Bohr models. Okay, so let's go over this. Well, obviously, I kind of like made this one bigger, but also your lithium minus, right? You have more electrons. So, which means your electrons are repulsing or expanding the shell, which means it would have the greatest radius. So even though these have the same number of energy levels, this one would have the greater radius because it has more electrons here, kind of pushing each other away. And obviously with lithium plus, you can see it loses an energy level. So this would be the smallest one. And then out of these, which one would have the smallest radius? So again, let's just draw it out, right? So two of them I already drew. So lithium, whoops, hold on. Move this here. Move this here. Okay. So two of them I've already drawn. And then helium I'm also going to draw. So the issue here is helium also has 2 electrons. So obviously it can't be lithium regular. So it has to be lithium plus or helium. So now that you have the same number of energy levels, like before, look at the number of protons, right? So lithium has 3 protons and helium only has 2 protons. So since lithium has 3 protons, it has more protons, which means it'll pull the electrons closer, which equals smaller radius. So your correct answer should be lithium plus. Helium only has 2 protons, so it won't pull your electrons as closely. So again, when you're doing ionic radii, you need to draw the Bohr model and like use the reasonings here, because you can't just like memorize this because it has nothing to do with your ionic radii. You would have to kind of draw the Bohr models to figure out what's going on. Okay. Moving on, we're going to be talking about something called first ionization energy. So your first ionization energy is the amount of energy required to remove the first valence electron. And that's why it's called the first ionization energy, because you're removing that first electron. We'll talk about second and third ionization energy a little bit lower from here. So the greater the ionization energy is, the more difficult it is to remove an electron. And this is the trend for ionization energy. So basically, your highest ionization energy would be in this top right-hand corner. Your lowest ionization energy would be in this bottom corner. And the reasoning is pretty similar to what we did for atomic radius. So ionization energy is going to increase going left to right. And the reason why is because you have more protons, right, over here than over here. So if you have more protons, you're going to have higher Coulombic attraction. And if you have higher Coulombic attraction, that means since your protons are pulling the electrons more closely, it's going to be more difficult to remove those electrons. And then ionization energy increase as you go up because you have less distance or less energy levels as you move up in a column, which means that you have more or higher Coulombic attraction again. So it's going to be harder to pull off that electron. Okay, and one interesting thing to note is noble gases will always have the highest ionization energy in their period, or highest first ionization energy in their period, because since they have a full valence shell, it's difficult to remove an electron. So remember, it's most difficult to remove an electron from a full shell. And that's what the noble gases are. They have a full shell always. Okay, now why don't you guys try these questions here? Okay, so pretty straightforward, right? So ionization energy, what does it mean? It's the energy required to remove an electron. Distance from the nucleus, that's the atomic radius. And then which would have a smaller ionization energy? So you have sodium over here and fluorine here. So again, whatever's closest to this corner would have the lower or smaller ionization energy. So that should be sodium. And again, sodium has more energy levels. So since that distance is greater, it has less Coulombic attraction than fluorine over here. And then which would have the greater ionization energy? So you have chlorine, silicon, sulfur, and sodium. So chlorine is the closest to that top right-hand corner. So chlorine would be your answer. Okay, and again, also chlorine has the most protons out of these, so it's pulling those electrons, I guess, the most strongly. Okay, now let's get to second ionization energy or third ionization energy. This gets a little bit confusing, and again, I'm probably only going to ask like 1 or 2 questions on this on the test or quizzes, but it's more of like if you're going to take AP Chem, they like to ask this a lot, so I'm just prepping you in advance. Okay. So second ionization energy, basically the number of ionization energy determines or tells you which electron you're removing. So like I said before, first ionization energy means you're removing the first electron, right? So second ionization energy would mean you're removing the second electron. Third ionization energy would mean you're removing the third electron. So how can you know which ionization energy will be the highest? Because it's going to differ. So the ionization energy that is the highest is when the electron that you're pulling is from a full shell. So again, the ionization energy that is the highest will be when the atom has a full shell, or when the electron you're pulling is from an atom with a full shell. So let's go over this. Which of these would have the higher second ionization energy, sodium or magnesium? So again, like the ionic radius, what you need to do is anytime you get one of these questions, you need to draw the Bohr model, or else it's going to be hard to tell what's going on. Okay, so I'm going to draw these out for you guys. So sodium looks like this, and then magnesium, pretty much the same thing, except it has 2 electrons on the outside. Okay, so if I remove, since we're looking at the second ionization energy, we're looking at the second electron to be removed. So for sodium over here, this would be my first electron. And then one of these here, this would be my second electron. For magnesium, right, this would be my first electron. And then one of these here, this would be my second electron. Okay, so again, your ionization energy that is the highest will be when the electron is from a full shell. So kind of like a noble gas. So looking at this, I'm gonna launch the poll. Which of these do you think would have the higher second ionization energy? Okay, so I see kind of mixed results. So okay, so you see here for this second electron for sodium, this second electron is from a full shell, right? You see the second electron here is when the shell is complete or filled. Whereas this second electron here for magnesium is not from a full shell. So again, the electron that is hardest to remove is from a full shell. So this electron, or sodium, would have the higher second ionization energy. Okay, so your correct answer should be sodium. Another way to look at it is when the electron you're pulling is from when the atom looks like a noble gas, because noble gases always have full shells. That's also another way you can kind of think about it. Okay, so sodium would be your answer. And if this is kind of like difficult idea for you, then I would say, like, I'm just going to give you a little bit of a hint. So your noble gases will have the highest first ionization energy. So that means this column here, so group 1 would have the highest second ionization energy. This group would have the highest third ionization energy, and you can keep going. This would have the highest fourth ionization energy. This would be the fifth, sixth, seventh. So, I mean, again, if you just want to straight up memorize that, you can, but I would say it's just easier to like actually know why that happens. But I'm going to write that here for you guys just like as a little tip. Okay, so let's move on to our last atomic trends or periodic trends. So we went over ionization energy. Now the last one is electronegativity. So electronegativity is the tendency for an atom to attract electrons in a bond. Now, what's a bond? That's something that we haven't actually talked about before, but a bond is just when atoms are connected to each other. And how atoms are connected to each other is they use electrons. So you can see here, if you have two different atoms, one atom will most of the time pull the electrons closer than the other atom will. So whichever atom pulls the electron closer, that would be the higher electronegativity atom. And then the one that doesn't pull the electrons as closely, that would be the lower electronegative atom. So again, electronegativity is also kind of related to Coulombic attraction, right? So if you move left to right on a period, the atoms over here would have a higher electronegativity because they have more protons, so they want electrons, or they can pull electrons more closely. And then electronegativity will decrease going down a group because, again, you have more energy levels, right? So then the protons can't like attract the electrons as strongly. And then this is just electronegativity of common elements. So this is just pretty like easy to remember. People look at it as Fonkelbrish. So fluorine would be the highest electronegative atom, and then hydrogen would be the lowest electronegative atom for these elements. It's not saying that hydrogen is the lowest electronegativity of all elements. It's just saying for the ones listed here. Okay. So that's electronegativity, and one exception is noble gases. So noble gases have zero electronegativity. So technically, fluorine is the corner with the highest electronegativity. So noble gases have zero electronegativity, again, because they have a full outer shell of electrons, so they never want more electrons. So they're never going to participate in a bond and they'll never pull electrons in a bond because they're never going to form a bond anyways. They have a full outer shell, so they don't need more electrons. Okay, so noble gases are an exception to the rule. So the highest electronegative atom would be fluorine. The lowest would be francium. Okay, so let's launch this poll and then we can finish up. Okay, so which of these elements has the highest electronegativity? So obviously I have been saying fluorine has the highest electronegativity, but it's also on that closest to that top right-hand corner. And then which of these would have the smallest electronegativity? So we have fluorine, iodine, cesium, and sodium. So you can see cesium is closest to that bottom left-hand corner. So cesium would have the smallest electronegativity. And then number 3 is kind of a trick question. So like I said before, right? Noble gases have 0 electronegativity. So if you look here at argon, argon's a noble gas. So no matter what, it doesn't matter what the other elements are, argon is going to have the smallest electronegativity because it's a noble gas, right? So it doesn't even matter what the other elements were. Okay, and then here's kind of a summary of the chart. So if you want to look at this chart, you can, but basically I just memorized the corners. So atomic radius would be the highest in this corner. And then ionization energy is the highest, or at least first ionization energy is the highest in this top right-hand corner. And then electronegativity is the same way, except it doesn't go to the noble gases. So electronegativity is the highest in this corner. And that's kind of how I memorize it.